revisit the concept of function transformations and look at all the transformation examples using an exponential graph and a logarithmic graph. So let's start with a simple exponent graph, 2 raised to x. The base is a number greater than 1 and the index or the exponent is a real number, which means it can take all values, positive, negative, fraction, 0 as well. We are going to look at only graphs with positive base. It can be a number less than 1 or greater than 1. 0 base doesn't make any sense because 0 raised to anything will be 0. So positive base only. And let us try to understand this graph. So 2 raised to x means 2 is multiplied with itself and x tells us how many times. And well, when we say multiplying with itself, x being a real number seems odd, but what it really means is if I do 2 raised to 1.5, it means it's 2 raised to 1 times 2 raised to 0.5, which means 2 is multiplied by root 2. So this idea of real numbers as an exponent means that you are looking at not just the powers, integer powers of a number, but you are also looking at fractional powers which are possible, which means roots of the number, right? So that's how x is a real number. If we look at the graph simply appears like this. It's easy to understand that at x equal to 0, 2 raised to 0 or anything raised to 0 is 1. As x becomes more and more positive, 2 raised to x will start increasing, right? And on the left hand side, when x is negative, let's look at some of the values. It's 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, which means it's 1 upon 2, 1 upon 2 square, which is 4, 1 upon 2 cube, which is 8, and so on. So the numbers are becoming smaller on the left side and they are becoming bigger on the right side. So that is the basic graph of an exponential function. And the left hand side, though it decreases, it never reaches 0. So it only approaches 0. The other name for this kind of behavior in mathematics is asymptotically approaching 0, reaching 0, and therefore y equal to 0 is the asymptote. What kind of asymptote is it? It is a horizontal asymptote. Why is it horizontal? What it means is end behavior of the function. When x takes very large negative values, the function, the y value approaches 0. That's why it is a horizontal asymptote. We will also be looking at another asymptote called vertical asymptote in some time. But remember, horizontal asymptote always means where does the function reach when x takes large values, either in the positive direction or negative. In the positive direction, for example, as x increases, y also increases. It is not reaching any value. It is going on increasing. So therefore, there is no asymptote on the right side of the x-axis, which means for x greater than 0. For x greater than 0 region, there is no asymptote. Whereas for x less than 0 region, the function is trying to reach 0. Therefore, there is a y equal to 0 asymptote. Okay. The first transformation I want to see is, if I think of a exponent as a raised to x, where a can be any positive number. A belongs to positive real numbers. Then what happens as a changes? That's what I want to look at. So that's my first transformation really. And let us look at some of the graphs. So I want to look at first all numbers greater than 0. So 2 raised to x, 2.2 raised to x, and then 3 raised to x, 3.5 raised to x and so on. So as I'm increasing the base, all numbers I'm looking at greater than 0. What are you seeing is that the graph is approaching closer and closer to the y-axis as the base increases. What is it indicating? If a graph is approaching closer to y-axis, means it's becoming steeper as a increases. Now here a is greater than 1. That's the first thing we start with, and as a increases, the graph becomes steeper. And becoming steeper means coming closer to the y-axis, and you can easily see here that the purple graph is the closest to the y-axis, and that is the largest base possible. Fine. Let's look at the next kind of transformation. So a raised to x plus b. So I'm keeping a constant. Let me change b. And what kind of a number is b? B is again a real number, and now there is no positive real number. B belongs to real numbers. So it can be positive, negative, 0, fraction, anything. So I'm going to keep a constant for some time and keep changing b. So let me look at the graph and add a constant here and see what happens if. So we'll have to zoom in and see what happens when c is becoming negative or c is becoming positive. What we are seeing is that the entire graph is moving up or down how much ever. For example, if c is 7, okay, let me also graph y equal to 7 line. The reason I am doing this is to show you that while the graph is getting shifted up 7 units because there is a plus 7, the horizontal asymptote, which was y equal to 0, has also moved to y equal to 7. So now the graph, it was 2 raised to x plus 7, will now move up. When you draw this in your exam, it's a sketch. So what kind of evidence are you going to show to the examiner to say that you have drawn it correctly? 2 raised to x plus 7 is moving up. So the y-intercept should now be 0, 8 instead of 0, 1. And the horizontal asymptote has to be y equal to 7 instead of y equal to 0. The shape does not change. It's only a vertical translation. So nothing changes as far as the shape is concerned. It still looks like 2 raised to x. So if we want to graph 2 raised to x as well on this, you will realize that the rate of change is not changing. The graph is growing at the same rate. It is not becoming steeper. The reason the red graph is on the right and on closer to the y-axis is because there is a vertical translation. It has moved up by 7 units. So here there was a y-intercept of 1 and now there is a y-intercept of 8. There was a horizontal asymptote of y equal to 0. Now there is a horizontal asymptote of y equal to 7. Okay. That's the second transformation. The next one is, if I look at a raised to x some b times a raised to x plus c. So I now know that this plus c is going to translate. What does this b do? Correct. So for some time we will exclude this vertical translation and only focus on what does this number b do to a raised to x. So instead of multiply or adding, let us multiply the number and see what happens to the graph. So as c changes, for example, c is right now 7. 7 times 2 raised to x. The first change we saw is in the y-intercept. Y-intercept is no longer 0, 1. It is 0, 7. Okay, what else has changed? Let us see by changing the value of C, make it smaller. As soon as it becomes negative, oh, it is getting reflected. Till the time it is positive, increasing C is bringing the graph closer to the y-axis, which means steeper again. Does it change the same way that it makes it steep with the change of base? Let's see. So I'm going to change C and so when I change C in the base as well as as a multiple, both of them do similar things. They make the graph steeper as long as C is greater than 1. As soon as C becomes less than 1, obviously the graph changes in its form. But so C is again here. If I think of a number getting multiplied with the exponent, this number is controlling the slope. Very similar to how when I changed the base, it was changing, but there are differences here. That first is that C can be negative, the base cannot be negative, and when it becomes negative, it is causing a reflection to happen. Look at this. If I make it negative, the graph will be reflected on the y-axis. Correct? And therefore, I need to think of it as not just making it steeper, but it is also playing a role in reflecting about the x-axis. So there are two things that it does. It can be negative, and it also causes a reflection about the x-axis when C is negative. Okay. So together, a general form of exponential function. What is general form? Like for example, in a quadratic equation, the general form of quadratic is ax square plus bx plus c equal to 0, where a, b and c are real numbers and a cannot be 0, then otherwise it's not a quadratic. Similarly, a general form for an exponential function is a times b raised to x plus c. What does a control? We just saw a is controlling the slope, and it sometimes causes reflection if a is negative. What does b cause? B always has to be positive. B has to be greater than 0, and b controls the slope. It decides how steep or what is C looking at? C is the vertical translation, and it also changes. The horizontal asymptote also moves along with it. So horizontal asymptote is also going to be decided by the C. One more transformation which we are forgetting is, what if x gets multiplied with a number? What kind of transformation that happens then? It is more like a horizontal stretch or compression. Let's look at that and then conclude. So we have a times b raised to x, but we are assuming that x is never multiplied with anything. What happens in that case? So I'm again going to start with this, but now c is here, and let me also graph the main function 2 raised to x and see what happens when c changes. When c becomes more and more positive, it is growing. When c is decreasing, it is becoming less and less steep. When c becomes negative, it is reflection about the y-axis. Okay, why is this happening? Let's see that. So say for example, it is 2 raised to 2x. Well, 2 raised to 2x is also same as 4 raised to x. So by adding a number here, it is same as changing the base. And what was changing the base doing? Changing the base was controlling the slope. It was making it steeper or less steep. There is another way of looking at it. Okay. For x is equal to 0, this is 1. For x equal to 1, this is 2. For x equal to 2, this is 4. For 3, it is 8. If I want the same y values, if I want 2, I only need x as half. If I need 4 as the answer, I only need x as 1. If I need 8 as the answer, I only need x as 1.5. So what is happening essentially is in 2 raised to 2x, at half the value of x, I'm getting the same y value. So it can also be thought of as horizontal compression. For a smaller value of x, I'm getting the same value of y. Yes, it is similar to saying it is becoming steeper, that's correct, or it is horizontally getting compressed. So if you look at your graph again, I can think of it as steeper, but I can also think of it as getting compressed along the horizontal axis. If you look at the red graph carefully, then that's what I'm saying. When I'm making C lesser than 1, it is like dilation, stretching on the horizontal axis. And when I'm making C greater than 1, it is compressing it along the horizontal axis. So that is how you can understand the transformation. Again, let me write again the general form. So instead of writing a times b raised to x plus c, I can also think of it as, when I say b, b takes into account numbers getting multiplied with x also. So it takes into account the horizontal compression and stretch as well. And that's why this is the general form of the exponential function. Right? It addresses all the kinds of transformations that can happen. So when I say b raised to x and b raised to minus x, it is a reflection about the y-axis. And when I say b raised to x and minus b raised to x, it is a reflection about the x-axis. If you have any doubts, let's look at it. It's 2 raised to x and 2 raised to minus x. It's a reflection about the y-axis. And if I look at minus 2 raised to x, it is a reflection about the x-axis. So that's the difference between. What about mod? What if I do absolute value of 2 raised to x? Well, what absolute value does is, the graph is any case only positive. So absolute value is making no difference to it. If I make this into absolute value, then it is going to reflect everything about the x-axis, because all the negative values will become positive. Right? So there is no difference at all between these. Let me also show you, if it is 2 raised to x and 2 raised to absolute value of x. What is the difference between the two? When I do 2 raised to absolute value of x, the function never sees negative values of x. Even if I give minus 2, it thinks it has got plus 2 and it gives you the same y value as plus 2. If I give plus 4 or minus 4, the function gives you the answer of plus 4 only. So whatever is on the right side comes left. Let me graph this and show you. So when I do 2 raised to absolute x, whatever is on the right side, the way it behaves, the same way it will behave on the left side, because absolute x removes the sign. So the function does not realize that it has any negative values of x. That is how you understand the function absolute. Okay. We will now look at the logarithmic function and understand the transformations similarly. So let's start with the parent function. We'll start with ln x. When I say ln x, it is log x to the base e. What is e? E is the Euler's number. It is an irrational number whose value is 2.718 dot dot dot. Why do we think of this number? Well, because any natural continuous growth, like the compound interest with 100% interest and compounded n times, if n becomes very, very large, so n approaches infinity, this will approach e. That means it's saying that whenever anything is compounded continuously, or it is growing at every second almost, then the base can be thought of as a natural number e. That's the importance of the Euler's number. We had given you an article to read about Euler's number, so you understand why this is taken as the base. Also, we know that e raised to x can be written as, so I can write e raised to x ln 2 as 2 raised to x, because e and ln are inverse operations, so they will cancel each other, and so that means e raised to x can be expressed as any other base by multiplying it suitably with a scaling factor, like e raised to x ln 10 is nothing but 10 raised to x. E raised to x ln a is a raised to x, and so on. So that's another importance of e, that it can be used in place of any other base by multiplying it suitably with a scaling factor. That's why. So let us start with the graph of ln x. Ln x is the inverse of e raised to x. So if e raised to x has a y-intercept of 0, 1, ln x has an x-intercept of 1, 0. E raised to x, it has a horizontal asymptote of y of the x-axis. Ln x has a vertical asymptote of x equal to 0. What does vertical asymptote really mean? We saw what horizontal asymptote means. Horizontal asymptote talks about the end behavior. Where does the function go when x becomes very, very large? What about the vertical asymptote? Vertical asymptote tells us when does the function become undefined? Which value of x can the function not take? So ln of 0 is a wrong thing. Why is that so? Well, e raised to x can never become 0. So the output of a exponent cannot be 0. Therefore, input to a log cannot be 0. They are inverse of each other, right? What is the output of exponent becomes input to the logarithm. That's why if output of exponent cannot be 0, then input to log cannot be 0. So there is nothing called log of 0. So if you graph ln of x, then like we showed you, you will see the x-intercept and you will also see the vertical asymptote. That means the x value can go as close to 0 but not become 0. So x belongs to real numbers, but x cannot be 0 and x cannot be less than 0 also. So for ln x, the domain is x greater than 0. Again, look at the graph closely and you will realize for values of x between 0 and 1, the ln value is negative. And for values of x greater than 1, the ln value is positive. What does ln give you? Ln gives you the opposite of exponent. It tells you the index of the exponent. So you know for values less than 1, if you graph e raised to x, for all values of x negative, didn't you have value of e raised to x as less than 1? So the output was less than 1, that time input was negative. Here when input is less than 1, the output will be negative. So they are inverse of each other. So whatever happens on the output happens on the input for log. Output of exponent is input for the logarithm. Output of exponent is input for logarithm. That's the way you have to understand it. Okay. Now let's start changing the base. The way we changed base for exponent, we will start changing the base for the logarithm also. We made 2 raised to x, 3 raised to x, and we saw something. So here I'm going to take the bases different and then start. So I'll make it log of x to the base 2 and then I'm going to use log of x to the base 3. Oh, this is base 10 actually. And so let me make it log to the base 3. Log to the base 4. And now let's see what is happening. So I'm going to remove log x to the base 10 for some time. And the base is not defined, it's 10. So as the base is increasing, 2 is the blue one, 3 is the black one, and red is the base with 4. As the base increases, the graph is coming closer and closer to the x-axis. Do you remember what happened on the exponent? When the base increased, the graph was going closer and closer to the y-axis. Now log is the inverse of exponent. So as the base increases, the graph will come closer and closer to the x-axis. Right? So behavior is matching in that way. So what kind of a translation is that? So log of x to the base a, where base can be only positive. Remember in exponent also we said base is only positive. So only positive base, but base can be less than 1 or greater than 1. That is fine. So if the base was less than 1 in case of an exponent, let's see what had happened. If instead of 2 raised to x, I had half raised to x, it would reflect on the x-axis. What happens if same thing happens in the case of logarithm? So instead of log of x, if I have log of x to the base 0.5. So the reflection was happening along the y-axis for exponent. The reflection happens along the x-axis for logarithm. Again, similar, if you want to match what happens on the exponent and the logarithmic side, you will see that it simply reverses the axis because they are inverse. So what was x becomes y and what was y becomes x. That is the reason this kind of behavior is being shown. So your base controls your steepness. It's becoming closer to the x-axis or farther. And the base also changes the reflection. Okay. What happens if I have a times log of x to the base b? Like we did a times b to the power x in exponent. What happens here? Let's change that and see. So we will start modifying not the bases, but what is multiplied with the base. So if I'm increasing, it is becoming steeper. If I'm decreasing, it is becoming less steep. And of course, if it becomes negative, then it is a reflection above the x-axis. So the C value is controlling, or this A value is controlling the slope. And it also makes it reflect if it is negative. Very similar to what it did in the exponent case, right? What if I have a log x to the base b plus c? Some value. Some not only multiplying but also adding. Then what happens? Let me remove this for some time and only look at the. So there is a vertical translation, but I'm seeing it very differently. I'm able to see that it is going down and less, but what can the examiner see when I'm showing vertical translation in case of a logarithm? If you pay attention, the x-intercept is changing. The shape does not change, but how does the examiner know that you have done it correctly is you show the correct x-intercept. For every given value of c, when the vertical translation changes, you can show the change in the x-intercept. Otherwise, the shape remains the same. It doesn't change at all. The only change is in. Same thing you did when you were looking at an exponent, if you remember. The vertical translation is what we were showing by showing the y-intercept. Now we are going to show the translation by showing the x-intercept. You can see the translation if you draw both this as well as the original function. If you now change C, you can see the vertical translation better. But in the exam, you won't have both the graphs. So what you can do to show the change is mark the label the x-intercept, and that will show your vertical translation. So this is as far as transformation is concerned. You have to understand f of x plus b as a vertical translation. If it's positive, it goes up. If it's negative, it comes down. F of x plus a. Let's look at this transformation with the logarithm. So instead of adding outside, what happens if I add it inside? And now if I change x, what is happening? Well, what is happening is it is changing the vertical asymptote for my function. So x equal to minus 2.6. Minus 4.6 is the vertical asymptote. Do you see the value of c is 4.6? If I change, my vertical asymptote keeps on changing. Do you see the vertical asymptote and the x-intercept, of course, will change if I change the value of c, and this is horizontal translation. You can see that with respect to the x, the green graph, that you're horizontally translating. So that's your horizontal translation. A times f of x is vertical stretch or compression, so your y coordinates change. And f of ax is your horizontal stretch or translation. Here the x coordinates change. If a is greater than 1, x lesser value of x will give you the same value of y. Finally, f of minus x is reflection about the y-axis. Minus f of x is reflection about the x-axis. So for every function, this remains the same. Of course, you have to show it differently based on whether you are showing changes in the asymptote or the x-intercept or the y-intercept and so on.